Okay, so I'll start off with the Composer module that we are developing at AU and give some details about this. So first, a very brief introduction to Composer, which we've been working on over the last few years. It's a visual programming language, node-based, in which you can see that you sort of generate what we call flow files, and you can have set up a Hamiltonian and a kinetic energy, and then you can have visualizations there. And what we think is nice about this is that it's dynamically reprogrammable, which means compared to the apps which is sort of a frozen interaction, which you integrate with, you have the possibility here of dynamically reprogramming the interface, you being either an instructor or having the students themselves develop something for that. And we have a number of publications sort of demonstrating that the utility of that. We have over the past years been working on developing exercises for Quantum Composer at high school level, introductory bachelor level, and at sort of bachelor graduate level, and for some research applications. And this can all be found sort of publicly available at a site quatomic.com. So I'll talk a little bit about what we are intending to be developing in the DDQ module, specifically tailored towards quantum technology. And so just as an illustration of how it works, here's sort of a quick illustration of spectra. And so you set up your flow file, you get then the spectra, and it's a single place where you have to insert in order to go from a harmonic potential like this to an infinite well like this, and then you get the energy structure of that. And that allows us then also to have an inquiry-based exercises where we say, type in, instead of x to the second power, type in x to the fourth power, and maybe start to predict before you do that what the energy spectrum is going to look like, and then type it in and then respond and understand how it is. And you could also take a linear one and see whether it sort of slots in between the harmonic and the infinite well, or on the left side or the left right-hand side of those. So you sort of get an intuition about the sort of visually get an intuition about the importance of the landscape to the energy structure. And then the second thing is sort of the dynamics, where you get the energy states out here, so the first, second, and third energy levels, and you can then make superpositions of those. And for instance, you can make an even superposition of the ground state and the first excited state, and then you will see that this is constructive interference on the right-hand side, destructive on the left-hand side, which means it's a blob which is on the right-hand side. And then you press go, and then the time-dependent Schrödinger equation will be solved, and it starts sloshing. And so you sort of get an intuitive information about that. And we'll see some applications of that sort of later on when we start talking about the courses that it can go into or the applications. Then sort of we're looking into the quantum engineering, control, and quantum technology applications. So that means it really is meant to be something that is, as I said, reprogrammable and reconfigurable to whichever need it is, and to give that visual understanding and a playful or exploratory way of understanding it. So here's an example of what we are developing for the DDQ, and that is Composer as a bridge builder between, in this case here, quantum computing and sort of the gate paradigm, where there are algorithms and there are sort of circuit diagrams like this. And you can have Qiskit, where you can be investigating that. But then the question is, how do you communicate to people who may not have a physics background what people are talking about when they're talking about quantum engineering and qubits and the protection of qubits to decoherence? So what we do here is that we sort of introduce a number of hardware paradigms of solid-state qubit architectures, and we just sort of flash these and then say, okay, each of those has a potential landscape associated with it, and then you can start to investigate what the energy level spacing looks like, and you can start to understand how engineering the Hamiltonian or the electrical system diagrams is going to influence the level spacing, and then influencing level spacing then also influences the protection of the qubit. And then we take the two smallest ones and say, that's everything that you can do in Qiskit. So it's meant to be a very quick introduction to how those can be bridged together. There's also from single to double well systems, so you can sort of start to add this, and then you sort of see what happens. And again, quantum tunneling appears because I take the superposition of a ground state and first excited state, and I press go, and it starts to tunnel. And depending on the energy level difference that you have, then that energy, that tunneling is going to be faster or slower. So in terms of quantum technology, a couple of applications of that is you just quickly add a third level here, and then you will have atomtronics, where you have sort of a single atom transistor dynamics. And you could also add level by level or well by well, and then you get multi-well, and you sort of get a band structure appearance of that with the bands there. And we can start to relate that to an atom which is initialized here, or an electron that is initialized and starts to tunnel around. So it's a way not to do all of the complex quantum simulations that you're doing, but to illustrate some of the really hands-on, some of the principles about a tunneling parameter or something like that, which goes into the Hamiltonians. Band structure, we can sort of illustrate, and we can start to take a plane wave or a pseudo-plane wave, and we can start to see the emergence of that sort of bottom-up, or discovering the kind of physics that is going on maybe in solid-state physics. So in general, what we try to do is that we take each of the modules, and then we try to look at, or the sub-modules, and then we look at the competence framework, and we sort of say, okay, what is it that we can support? What is it we cannot support at the moment? And as Simon said, we try to have a dialogic approach where we can then work together with the lecturers and say something is still not inside of Composer, or there's a visualization lacking. And here's an example where we work together with a team of researchers and educational researchers to develop a block sphere visualization, and then that feature was also there. And so that shows that feature. So that's an open invitation to either make use of some of the tools that are being developed, or come up with some applications where you think that we could be interacting together, and we will be happy to iterate that with you. Thank you very much.
Thank you, Jacob. Does anybody have any questions for Jacob? Paolo, nice to see you.
Yeah, thanks. Jacob, are there some limitations about the potentials that can be visualized? And what is the typical computing time?
So it's pretty real. So this is built on a simulation engine that we call Q engine underneath, which is C++, and so it's pretty fast in that sense. So you get real-time computations of it. Of course, the limitations that you can say is that maybe you have a grid of 512 spatial points, which means if you want to have 20 wells and you want to say, let's do block oscillations, and you want to do that, you tilt it, and then you want to see it going up and down, then the fidelity of the kind of individual eigenstates is going to decrease the more granularity in the potential that you have. But you could in principle do it. You could in principle set, we have done research exercises where they sort of are given a control exercise and a research relevant exercise as a student exercise, and then they may have to do more. But usually all of the time dynamics doesn't have much lag in it.
But can you do something like the James Canning Godin model there?
Well, so this interface is primarily focused on wave dynamics. So the single particle time-dependent Schrödinger equation, both Einstein condensates can also be included, but we sort of focus on that visual wave function approach to it, and then there's various aspects where you can sort of match it to a paradigm, like a James Commons paradigm, in a certain sort of approximative domain. But it's not meant to be an all-inclusive. It can simulate any kind of system, but really to sort of focus on what is it that students would be valuable in saying, okay, what is the evolution of the wave functions, and then to be able to relate that to some of the other models, which have their own, you can say, complexity or simplicity. No.
Thanks. Very nice, anyways.
John.
Yes, hello. Thanks, Jacob. Very nice. I think we talked about this at some point, but I don't remember what was the outcome. So some of these things, I mean, this is very advanced, but it can be very useful also for undergraduate. So I don't know if either, I don't know, maybe some master students in the DGQ that are doing TAing also themselves, but to use this material and you can use it for undergraduate courses.
Yes, so what we would like, we will be trying to develop also, you can say, a small module, which is like a visual, let's say a 3-hour visual introduction to quantum phenomena. And so, you know, basic quantum phenomena that is suitable for engineers or for, and we have been doing that for nano students and trying it out. So, and I think that works pretty well, where the mathematical background goes a little bit in the background, and or at least doesn't come first.